give you a warning. And go ahead.
Okay. Yeah. Hi, morning, everyone. I'm Zhaozhou Li, a postdoc with Avishai. I'm just starting a new position at Nanjing University, so apologize for not being there in person this year. I'm giving this talk on behalf of Avishai, which is a great honor. Avishai unfortunately couldn't travel and is having some voice issues. So he prepared the slides and is here on Zoom to answer questions after the talk. Today I will talk about feedback-free starbursts, or FFBs for short, a series of work done by these great collaborators, and many of you are in the audience. I will present the core idea of and predictions of FFB around the redshift 10, and then talk about the implications for the formation of supermassive black holes and quiescent galaxies around the redshift 5. Okay, so the story starts with a surprising finding from JWST, an apparent excess of bright galaxies at high redshift. This implies that the early star formation was far more efficient than we previously thought. We argue that feedback-free starbursts, or FFBs for short, can naturally occur in the most massive halos at the redshift 10 for their high gas density and low metallicities. The global star formation efficiency, which is the fraction of baronic mass turned into stars, can be very high. In contrast, at low redshift, is typically below 10% due to the stronger feedback. In these high redshift massive halo stars formed in thousands of dense clumps on a time scale of 1 million years with very high volume and surface density. The core idea is simple. So if a gas cloud collapses faster than the stellar feedback can be strong, then the star formation proceeds with very high star formation efficiency freely. This requires a critical density of around 3,000 per cc. But several more conditions are needed. The surface density must be high enough for self-gravity of gas clouds to beat the radiative pressure. The gas must cool fast enough on the Freeport timescale, which is possible at the same critical density of 3,000 per cc with a non-zero metallicity. And self-shielding. The cloud must be thick enough to protect itself from the supernova winds and the UV radiation from the previous formed stars. Finally, the halo mass should be below 10 to 12 solar masses to avoid hot CGM, so that cold streams can penetrate through the halo and supply fresh gas for efficient star formation. Now, let's take a closer look at FFB galaxy. The cold radial stream bring in fresh gas and encounter the stellar wind, the supernova wind generated by previous star formation. So in the shocking region with enhanced gas density, the gas fragments and collapse due to density instability. They are the FFB clumps that form next generation of stars. If the string has some angular momentum, similar bursts can be triggered by thermal instability in a gas disk. Using a steady wind model, we estimate that the wind velocity to be around 1,000 kilometers per second, together with a low gas fraction and a low metallicity in general. The FFB scenario naturally leads to a bursty star formation histories, as you can see here in the cartoon. Each FFB burst lasts several 3-4 times, around 2 million years each, until the gas is either used up by star formation or cleared out by feedback. The galaxy then needs about 10 million years to reaccumulate enough gas for triggering the next generation of burst. So this duty cycle means that while the average star formation rate might be around 60 solar mass per year, the peak rates during the bursts are significantly higher. When do we expect FFB galaxies? In this diagram of redshift and halo mass, we expect the FFB conditions are satisfied above a critical mass threshold beyond the redshift 7-ish. This threshold is about 10 to 11 at redshift 10 and lower at higher redshift. Based on this scenario, we build a simple model for galaxy formation with enhanced star formation efficiency in the FFB region and a smooth transition back to the standard empirical model universe machine. We made a bunch of observable predictions with our model. Here is the cosmic star forming density as a function of redshift. The orange curve shows the FFB prediction with a maximum efficiency of 0.2, and the blue with efficiency of unity. We see here the FFB model with efficiency around 0.3 aligns well with the JWST observations, while the pre-JWST model universe machine seems too low. Here shows the UV luminosity function at redshift 9 to 16. Again, the orange and the blue for FFB galaxies with efficiency of 0.2 and the unity, while the gray curves are the pre-JWST models, the universe machine and the Santa Cruz here. Now let's add the JWST observation data. As you can see, the FFB model with a maximum efficiency of 0.3 aligns well with the JWST data points in general, while the older models are too low. Now we are testing the model details with zoom-in simulations of the most massive halos. This initial results from Zach and Roman show that feedback is unable to destroy the high-density gas, and we see clumpy morphology and hot disk. I'll emphasize that this is just the beginning. We will ultimately need a 1 parsec resolution to fully resolve the FFB clumps. The star formation history from this simulation is also consistent with our toy model. The bursts are separated by about 10 million years over a total FFB phase of 10 million years with high efficiency. Lastly, the observation indeed show a clumpy morphology for high redshift galaxies, as shown in many literature, was consistent with the FFB scenario and the simulations. Now it turns out these dense clusters are not only be good for forming stars, but also for growing the seeds of supermassive black holes, which is the topic of the second part of my talk. I will quickly discuss how FFB scenario might help black hole growth. JWST found that black holes at redshift 5 are already very massive, reaching 10 to 7 to 10 to 9 solar masses. Strikingly, their mass is up to 1% of their host galaxy's stellar mass. That's 30 times higher than the local relation shown in the green. So the big question is, how did these black holes grow so big and so fast? We propose that the FFB provide a natural channel for rapid assembly of massive seeds. The basic idea is this: FFB galaxy produce thousands of dense star clusters, each of 10 to 6 solar masses. Inside each cluster, core collapse and stellar mergers form a very massive star, which soon collapse into a black hole seed of 10 to 4 solar masses. The key is that this must happen within 3 million years before the supernova explosion. Otherwise, the stellar mass black hole are hard to merge. The faster core collapse can be greatly boosted by the stellar mass spectrum and by the cluster rotation. Next, as these clusters dissolve into a stellar disk, there are intermediate mass black hole seeds sink into the galactic center and via the dynamic friction and merging into a central supermassive black hole within half gigayear. The stellar disk is important because the friction is much stronger in a disk than in a spherical system. But there is still a major challenge. The recoil from the black hole mergers could eject the remnant of the merger from the galaxy. One possible solution is that a compaction event depends on may deepen the potential well enough to keep the growing central black hole in the center. If you want to know more details about this scenario, please don't miss Juba's talk on Friday. Now for the final part, let's take a look at what happens after the FFB phase and how this might explain the quiescent galaxies seen at cosmic morning. JWST observations reported abundant massive quiescent galaxies around the redshift 5. Here, this plot shows their star formation histories. Taking the orange one as an example, it has a high star formation rate peaked around redshift 10, followed by a rapid long-term quenching at redshift 8 until being observed at redshift 5. Similar trends for the several other galaxies. These galaxies are massive and had bursty star formation histories peaking around redshift 10, which reminds us about the FFB galaxies. Furthermore, observation also shows that these galaxies are compact with high surface density, and they are very abundant, about 10 to 100 times higher than the pre-JWST model predictions. All these features point to a possible connection with FFBs. As we have seen earlier, we expect FFB galaxies at high redshift and high mass halos. Thus, the FFB and the non-FFB halos present a bimodality of evolution tracks depending on the halo mass. These blue curves follow the typical halo growth histories. Halos above 10 to 10.5 solar mass at redshift 10 can enter the FFB phase at redshift 11 and get quenched around redshift 8. Then they become the massive quiescent galaxies we observed around redshift 5. While for a less massive halo, they never undergoes FFB phase, but has a more mild gradual star formation history, likely becoming the typical star forming galaxies at the cosmic node. Therefore, there is a bimodality of FFB and the non-FFB halos separated by halo mass of 4 sigma peaks. What could be the quenching mechanism? These FFB halos are so massive that the supernova feedback alone is not strong enough. First, the quenching can start with the gas depletion due to the FFB burst and outflows. Weight compaction event can also consume the gas rapidly and prevent further gas accretion onto the ISM by supporting a gas disk and driven turbulence in CGM. Then the supermassive black hole can grow during the FFB phase, and the compaction events can then maintain quenching over a long time scale via AGN feedback. Yet a big challenge is to shut down the cold stream to prevent gas accretion into ISM. Here we consider two possible channels to shut down the cold gas streams, CGM turbulence and AGM photoheating. In the two plots, the location where the curves across the unity indicate the critical Mach number on the left and the luminosity needed to destroy the streams. Basically, we need either a transonic or even supersonic turbulence, possibly powered by AGN, or we need AGN photoheating. Sub-super Eddington luminosity might be enough if the gas cooling is slow, but super Eddington luminosity could be required for faster cooling to destroy the streams. based on an extension of our model, we made some predictions for these quiescent galaxies. They are massive with stellar mass above 10 to 9 solar masses, depending on the quenching redshift and halo mass. Their luminosity decays after quenching, and they should have an abundance around 10 to minus 5 per cube parsec, which is relatively constant across this redshift range and comparable to the density of observed black holes. In general, we expect these post-quiescent galaxies are massive and compact with active feedback, active black holes and outflows. In the final slide, I'm showing the luminosity function from redshift 4 to 25 and the contribution of each galaxy type, FFB, non-FFB, and post-FFB galaxies. So let's start at high redshift, say redshift 10. At cosmic dawn, the FFB galaxies shown in blue dominate the luminous end of the luminosity function, while the non-FFB star-forming galaxies shown in gray dominate the faint end, and similar for even higher redshift. At low redshift, say 6, after the shutting down of the FFB, normal star-forming galaxies become dominant at all luminosities. Nevertheless, the post-FFB quiescent galaxies, shown in green here, still can contribute to a significant fraction at the very bright end. By the way, we have improved the luminosity assignment in our model recently. It gives a good match to data of up to redshift 17. And beyond the redshift 20, both the observation and the models become more uncertain. Okay, now here is the summary. So we proposed a modality of FFB and non-FFB galaxies depending on the halo masses. In most massive halos, about 4 sigma peaks, the FFB galaxies have clumpy star formation with high efficiency and allow for a rapid black hole growth through the merger of massive seas. After getting quenched by compaction and maintained by aging feedback and stream disruption, the post-FFB galaxies might be observed as the massive quiescent galaxies at cosmic morning. And we, for all these scenarios, we have made observable predictions available with digital data tables. So you're welcome to compare with your observation or model simulations. Okay, I will stop here. Thank you.
Thank you. Any questions? And maybe say your name, since I don't think they'll be able to see who you are.
Zhaozhou know me well, so Fang Zhou asking question here. This is all great. Thank you, Zhaozhou and Avishai. This is more of a question to observers. Why are the high Z, ultra Z quiescent galaxies so interesting in the first place? I don't quite get that. I mean, you quench galaxies by mass quenching, morphological quenching, aging feedback. So all the processes can be operative at high Z, right? As long as you reach high enough mass, as long as your halo go into this hot CGM mode, hot mode, or cold streaming hot mode, if for some reason you disrupt the cold stream, you can quench a galaxy. Or starvation, your heavy node use up your gas. What's so interesting in the first place?
I guess the problem is that one, they are too massive. So because they have been quenched for a long time ago, you need a very efficient star formation in the past to make them massive at the time they get observed.
So
second, they are very abundant.
So it's still the high efficiency part that is interesting.
Okay. Yeah, and they are very abundant and about 10 to 100 times higher than the pre-GWST observations, predictions. I think that's why what makes their interesting, as shown here.
Right. This is Todd Lauer. This is really interesting. I wanted to ask a little bit about the supermassive black holes. So I understand you're building them up with a hierarchy, which seems quite reasonable. I'm not sure I understand, as it were, the need to suppress the recoil, and I wonder if that's actually something you can leverage to explain a number of the observables. Recoils, depend very highly on a variety of conditions and can range from essentially nothing to several thousand kilometers a second. But it is a phenomenon which should occur, and you can transport, the supermassive black hole out of whatever protogalaxy you have there. Ultimately it may return if it's not, extremely high escape velocity. It'll carry some amount of stars with it that are closely bound. But if you're focusing on, the level to which you're actually right now seeing stars associated with supermassive black holes, I would think that you want to think very carefully about what the spectrum of recoils is, what happens with those recoils in the surrounding context of galaxies, what are the return times, and so on and so forth. And I think through that you can get maybe a better handle on what you expect to actually be associated with the black hole.
Yeah, thanks for the comments.
Okay, let's thank Zhaozhou and Avishai again.
Thank you.